Here we go. Last lesson of the chapter. We likely won't finish it today because when we do, well, we're doing higher derivatives as we talked about yesterday, which means we'll take the derivative of a derivative and maybe the derivative of a derivative of a derivative of a derivative of a derivative. But if you think about how much work was involved yesterday, what if we want to find the second derivative using implicit differentiation? It gets really long, so we probably won't get to that today. So that'll be Monday. Monday's planned in as a catch-up day, so we have the time. So we're good. Here we go. Some notation. Okay, we know if we're doing the derivative of y, we can write it as y prime. Derivative of f of x, f prime of x. Or derivative of y, dy dx if we use Leibniz's notation. And I'll just say his name different ways every time because I'm confused. And then here's an example if I do the derivative. Oh, dramatic. Second derivative, we use 2 primes. But then we have some weird notation here. I'll give you a minute to copy this down and then I'll talk about that. Yes? Yes? Because sometimes it's useful, because it's telling us the change in slope. So how is the change changing? Yeah, so if we think of position time, first derivative velocity, second derivative acceleration. And sometimes there's this branch of math which is pure math, which just does math for the fun of math. And eventually, often applications are found, even if there's no initial application discovered. Okay, are you with me and quietly listening? Suppose I want to take the derivative of y with respect to x. Yep. And then if I wanted to do the derivative of this, notice there are 2 d's on the top, but only 1 y. But there are 2 dx's on the bottom, which is why we have the 2 there and the 2 there. Okay, it's a notation. We're not really squaring things. It's just a notation to tell us I'm going to have 2 d's and 2 dx's. Yep. Well, yes, because we're thinking of it as the derivative with respect to x. Yeah. And eventually, we're going to get to a point where we break this apart into like a change in y over a change in x. But that's a little ways down the road. We're on the road to discovery.
Oh, that's tough.
Yes. Yeah, I didn't know where it was going to go, and I hope I'm going to come up with something good. Oh, discovery was not bad. I can live with that. Okay. So thanks for keeping me on my toes there. Excellent. The toe keeper honor. Excellent. Question? Shh. Pardon me? Chapter 3, all real life applications. Well, like we talked about, the easiest one for us to understand, and because of that, it's the one that comes to mind for me, is thinking position, velocity, acceleration, jerk. So jerk would be the change in acceleration. And you could keep going. I don't remember what it's called after that. I have looked it up, but I can't remember.
There's a word for it.
And there probably is. Yep.
Have we answered the first question yet?
Yeah, that's a good question.
We did actually on day 2. But now we're finding more ways to find slope of the tangent line. Third derivative. Notice what's happening to the polynomial part of my function. The exponents are getting smaller until they disappear, right? That x squared, first derivative had an x, second derivative had a constant, third derivative, that term's gone completely. So if it was just a polynomial, if we keep doing derivatives, eventually we're going to get 0. Question?
Is there a way to determine how many derivatives you could take of a certain function?
Sometimes.
If it's a negative exponent, would it always be infinite?
Yep.
But if it's a positive exponent, it would be the highest degree, right?
Probably one more than the highest degree.
Oh yeah, because you could move 0.
Yep. Yes. Shh. Sorry, once more. I will. There is no diploma. Yeah. But yeah, I will ask you, given a position time function, what's the acceleration? And you need to know it's a second derivative. But we'll talk about that more in chapter 3. So for this chapter, we won't. Okay. Suppose we have a mystery number of derivatives. We would call this the nth derivative. So the notation we use in this situation, after we have 3 primes, we stop with the primes. Because you have to count them. And so rather than counting, they'll use brackets and put the number in here, which means we have to be careful. If I have something that's written like this, is that just y to an exponent, or is this a derivative? So the context needs to tell us. It shouldn't be a problem for us because we're just doing derivatives, right? Yep.
What if on the side, I say y to the power of a number, or whatever, that n, it's like a Roman numeral. I just use a Roman numeral instead.
That would be kind of your notation. This is the accepted math notation. Yeah, you can make your own notation and see if you can influence the math world to adopt your notation. It could happen. Because we don't know how many derivatives we're doing, we have no idea what this function is going to look like. Okay. The most useful derivatives for us will be the first and second derivative. Third derivative isn't going to be super helpful other than entertainment as we play around with it. So first we have just the function tells me how y depends on x. What does the first derivative tell me? How y changes as x changes. This is the first derivative. So what does the second derivative tell me? How the slope changes as x changes. How the change in slope changes as x changes. Yes. So once we get to chapter 5, the second derivative is going to help us because if my second derivative is positive, that means my slope is increasing. So I could have a slope of 0 and it's going to increase. So it tells me my curve goes up like this. Even if I had a negative slope, if my second derivative is positive, it means it's going to increase towards 0. So my graph is going to curve in this direction. That's chapter 5. So let's just practice it a bit. And you know how to find a derivative, so find the first derivative and the second derivative for this function.
Fine. X, wait, no Y makes so beautiful, right?
Negative 2x, no.
Wait, the negative is with this one. You minus X.
Any questions with this example? Yep. As in this one right here. How I got to this one from the previous one. Okay. So I looked at these terms and those terms because they have constants and they have x's. So I looked to see I could get a 30x as a common factor for both of them. So that's what I factored out. So when I factor that out, then over here what I'm left with is still a 2x. Because I've taken a 2 from there, and I've taken a 15x from here. So I still had this 2x that ended up getting multiplied to that 3x squared. So that's why I had this 6x cubed left over. Yeah, so maybe it would have been clearer if I'd done more simplifying first before I did the factoring. Because I practiced a fair bit, I like to just factor at this point, but I maybe should put in an extra line. The rest of it is good? Fran? Okay, anybody else, questions? There we have the first derivative. Let's look at number 2 together, and then I'll give you more time on the rest.
Let's go.
Number 2, finding the first derivative, which I have in green over here. Everybody good with that? So we do, when we're going to do a second derivative, we typically want to simplify the first derivative as much as we can to begin with. Probably not a factored form, but an expanded form if it is reasonable. And then we can work on the second derivative. So here we have low, so there's low d high minus high d low. Square the bottom, there you go. And notice, often what we'll find is we're going to get a common factor. Oh no, what do I do? A common factor between the numerator and denominator, and one of those terms from the denominator will cancel out. So as we're simplifying, again, there's another reason why it's useful for us to put it in simplest factored form to see if there's a common factor, and there will be. So my next step looks like this, where I factored out common factors from the numerator. And we can see One of those will cancel with one of those, so I'll have 3 left in the denominator. And then I'll simplify that square bracketed part. Any questions? All right, I'll give you some time on the next couple questions. Number 3, we'll find a first 5 derivatives. Number 4, we'll find the third derivative. So here we have the answer for number 3. And what I wanted to highlight here, just with this 4 factorial, is that for the first derivative, I bring down the 4. Second derivative, I have that 4 and I bring down the 3. Third derivative, I have the 4 and the 3 and I bring down the 2. And then the fourth derivative, I have the 4, the 3, the 2, bring down the 1, and that's why we're getting 4 factorial here. Keep in mind that that all happened because this coefficient was 1 in front of the x to the 4th. If we had another coefficient, then that coefficient would be multiplied to this 4 factorial. All right, a couple more questions, and then we'll leave second derivatives using implicit differentiation for another time. Here we go. Pause the video if you want some time to take this derivative. If you have done it already, here's my answer. We want the third derivative when x is 3, so we can't plug the 3 in before we find the third derivative, because if we plug it in too soon, we'll have a constant, and the derivative of a constant is 0. So need to wait until we get the third derivative, then plug in the number. All right. Another question, simplest factored form. And yeah, so 2 questions. So I'll give you a minute. Well, pause the video, work through this question, and then I'll pull out my answer. First derivative requires the chain rule. Again, good idea to simplify it before finding the next derivative. Second derivative will require a product rule. So again, as a reminder, there's my first function. So I have the first function times the derivative of the second, and this whole thing is the derivative of the second, plus my second function times the derivative of the first. And then I'm looking to see what common factors do I have. So it might be helpful, as I mentioned earlier, to do some simplifying first. So if I did that 5 times 4 times 24, that would give me 400. Let's see what color. Blue is good. 400 x cubed times x cubed is x to the 6th. And then I have that bracket, x to the 4th plus 3 all to the 4th. And then my second term has the 72x squared, x to the 4th plus 3 to the 5th. sometimes this will make it easier. This time it doesn't actually make it easier because this 72 over here is 24 times 3. So I can see the 24 more easily as a factor there and here, and see that as I look at the 5 and the 4, there's not a common factor with the 3. So that's partly why I like to simplify sooner rather than later, but do what makes the most sense to you. So I'm going to factor out this 24x squared. Then here I have 4 of those x to the 4th plus 3's. There I have 5 of them, so the common factor is 4 of them. And then the leftovers, what color haven't I used? I'll use a light green. The 4 and 5 and the x cubed. Oh, and I had 1x left over here because I only factored out an x squared. So that's where this 20x to the 4th comes from. And then from the 72, I still had the 3. I had one of these 5, x to the 4th plus 3's, and that's where that comes from. Expand, collect like terms, and we have a simplest factored form. Again, pause the video, find this second derivative, and then restart when you're ready to check your answer. There we go. Pretty straightforward because we can just use the power rule twice. And that's where we'll stop for now. My next question, gets into implicit differentiation. So I'll save that for another video. Here we go. End of this lesson. Take care.